So Andrea,
okay. Okay, so I mean, we had some technical issues of any sort at this point, but I think we're facing a great chance of hearing Thiago speaking about his recent work, wave of work on integer programming for machine learning, especially for neural networks. So Thiago Serra has been got his PhD from Carnegie Mellon already, what, 3 years ago at this point, Thiago?
Yes, 2018.
Yeah, 3 years ago. So I was fortunate enough to be in his PhD committee, and I remember that very vividly, conversations with Thiago over the years about his research, a lot going on in cutting planes and various other techniques for integer programming. It always be for me very, very special and very nice to interact with the people at CMU, and especially with Thiago was a great pleasure. And I following up what his career and the great things that he's doing currently at Bucknell University, and the work that he's and going to present today to us on indeed integer programming for neural networks. Thiago, the floor is yours, and please.
All right. Well, good afternoon. Thank you very much for the introduction, Andrea, and Vahid, thank you very much for the invitation. So it's a great pleasure to be here. And today I'm going to talk with you about a problem that unfortunately I'm not going to have by giving this talk. Now, when I go to places like to give talks or to conferences, I buy books, I get stuff for my kids, and I often can't get all of these things back in my bag. And I'm not able to fit everything back in my bag when I have to go back. And well, I'm not in person, so that's not happening here. But the thing is, with neural networks, we may have the same thing. Sometimes you have to train larger neural networks to be able to do a certain task with the accuracy that we want. But we may not want to to lose that accuracy to make them fit in smaller devices like a cell phone, just to make sure that like this the models that we're training are going to be accessible for people who don't have as much resources. So I'm going to talk about what we can do about that. And this is joint work with Abhinav Kumar. He's a very sharp PhD student at Michigan State University, and Sri Kumar Ramaligan, who is currently working at Google Research in New York. Now, just 1 minute. So here we're going to think about feed-forward neural networks. So it's the most basic model of what a neural network may look like. And let's think about them as a function that's mapping from an input space, let's say X, to an output space, let's say Y. And I'm going to further assume that every neuron here is a rectified linear unit, which it turns out is the most commonly used type of neuron because it's simple enough that it's easy to train, but at the same time, it allows us to do very interesting things and to train very accurate neural networks. Now, in every one of these neurons with a ReLU activation, the output is going to be given by the maximum between 0 and an affine transformation of its inputs, which is basically the weights and the bias that we obtain as we train the neural network. And when we think about the analogy with biological neurons, we can say that the ReLU is inactive when the maximizer of this expression is the first term, and that the ReLU is active when the maximizer of this expression is the second term, in which case we have an output which is positive. Now, the question that I want to answer here is whether we can find a smaller neural network that models exactly the same function. So perhaps it could have fewer neurons, maybe fewer layers, but essentially we wanted to do the same mapping from X to Y. Now, we can make this question a little more convenient to address if we consider only inputs that are relevant for a given application. So let's say that our inputs X come from this set capital X, and those are the only inputs that we care about. So maybe there might be other inputs that would have different outputs in the neural network. but they're just not going to happen in practice. And to give you the most common example of something like that, here's the AIM-NIST dataset. It's basically a collection of 28 by 28 pictures of handwritten digits from 0 to 9. And in every one of the 784 inputs corresponding to one of these pictures, we're going to have a value between 0 and 1, depending on whether that picture is closer to black or white. So we're never going to see a negative value for a pixel or a value greater than 1. So it doesn't even make sense to talk about what happens to the neural network if we send an input like that through the neural network. Now, this is just one example of how we can use this, but it's going to be important here because when we talk about optimization over neural networks, having bounded inputs is going to be very important. Now, there's a lot of work in compressing neural networks, and there's especially a lot of work in what I denote here as inexact compression. And we care so much about compression because embedding neural networks in smaller devices is important. There's also an accessibility matter. And we know for a long time now that there is a lot of redundancy between network parameters. So if you pick a few of the parameters of your neural network, you're able to predict the value of other parameters. So that really encourages us to think about reducing the size, even if we're slightly changing what the neural network does. Now, we also know that if we approximate the neural network, if we use low rank approximations of the weight matrices of the layers of the neural network, we can actually obtain better generalization bounds. We obtain a compressed neural network that has better generalization. And also, we also know, and this is something mentioned in a recent survey, that there is this trade-off between compression and accuracy. The more you're able to compress a neural network, the less accurate this neural network is going to be. But there are some approaches that are actually lucky enough. I mean, it really depends on how you do these things, but there are some cases in which it's possible to recompress the neural network and the overall accuracy is as good as before, if not better. So there is some work in that, along those lines, perhaps like 5 papers at this point or more. But that brings us to the next point, which is compressed neural networks may be less robust. And even if the overall accuracy is higher or equal, you might have a loss of accuracy that's disproportionately distributed across classes or types of inputs. So what has been observed in the past with some extensive experiments is that when you compress the neural networks in certain ways, you're going to do an even better job in classes that you were doing a good job and a worse job in the other ones. So if you think about facial recognition, for example, it's an issue and a known fact that most of the software can correctly identify white male faces. But when you talk about black female faces, the accuracy is much worse. And when we do a compression, we might be worsening this discrepancy across different classes, which also raises the issues of fairness. Now, there is a lot here, and I'm not going to be able to cover all the possible papers on this topic, but there's an entire page in our preprint about that. What I'm going to mention here is that some of the recent work, and this is a growing body of work, is aiming at formulating optimization problems to help us identify how to compress the neural network. And the one that most closely relates to what we do in this work is this one here, which uses mixed integer linear programming as well, but in the context of inexact compression. So what these folks from Montreal are doing, and one of them is here right now, is they're identifying, they're assessing the irrelevance of different neurons to preserve the ones that are the most important for the behavior of the neural network. Now, I'm going to switch gears and talk about exact compression, which is relatively unexplored. And here's why we care about exact compression. We're going to, by doing exact compression, we're going to avoid the side effects that I mentioned before. So in this work by Sarah Hooker and others, we have seen that there's no free lunch. So as we're compressing a neural network and compromising part of it, we're going to have some side effects and they might not be desirable. And the other thing is, if we're doing an exact compression, we don't have to retrain the neural network because we're not doing any damage to the behavior of the neural network. Whereas if we're doing an inexact compression, we may need to retrain the neural network just to make sure that we have the right level of accuracy again. Now, what I have to say here is that this slide almost has no space left, but there is enough space that I can cover all the prior work on exact compression that I'm aware of, which is one paper accepted this year at ICLR on identifying symmetry in graph neural networks, and our work that was published last year at CPI-OR on compressing small rectifier networks. And that's the approach that we're scaling up here. With that said, let's talk now about how we're going to do this. So there should be a thread that I'm going to pull so that I'm going to magically reduce the size of a neural network without changing anything in the behavior. And that thread is the stability of ReLUs. So we're going to look at neurons in the neural network that are stable, which means that they only have one of the two possible states. And the first class would be the stably inactive neurons. Those are neurons that never produce a positive output. In other words, no matter which input X from the set capital X we send through the neural network, the output, the pre-activation output, which is just a fine transformation before taking the maximum between 0 and this expression, is always going to be smaller than or equal to 0. In that case, we know that the output is always 0, so we can anticipate that this is a case where we can easily simplify the neural network by removing the neuron. Now, we may also have neurons that are stably active. So those are neurons that are always going to produce a non-negative output. So no matter which input X from the set capital X we send through the neural network, when we get to this neuron, we're going to get a pre-activation output that is greater than or equal to 0, which means that the output is always equal to the pre-activation output in this case. And what's special about stable neurons is that basically we don't have a nonlinearity here because, well, in neural networks, we have the activation function. That's a nonlinear function applied on top of this affine transformation that we're seeing in the screen right now. And this is what allows us to express more complex functions with a neural network. If you just remove the activation functions, basically doing a linear mapping from neuron to neuron, you can basically collapse the entire neural network as a single affine function. So if we don't have nonlinearity, basically the neural network is not going to be very expressive. And actually understanding how expressive a neural network is something that we do through this theory of linear regions that I'm not going to describe here, but I'm going to show you some references at the end. But basically, we don't have this nonlinearity, and we're going to explore how we can leverage that to simplify part of the neural network. All right, so I'm telling you that there's this magical thing, and you might be somewhat convinced now that if we know that certain neurons are stable, we can do something about it. But we have to figure out how to identify that the neurons are stable. And as you might be anticipating, especially thanks to Andrea's introduction, we're going to do that by using optimization. We're going to look at two objective functions here. In the first one, we're trying to maximize the pre-activation output of the neuron by thinking about any possible input, valid input. And if by solving this problem, we find an output that's smaller than or equal to 0, that means that the neuron is stably inactive. We can never get something positive out of it. Whereas if by optimizing over all the inputs of the neural network, the pre-activation output, if we're minimizing, the pre-activation output is greater than or equal to 0, that means that the neuron is stably active. We can never get a negative value out of it. So the only way we can certify that is by solving an optimization problem. And in both of these cases, we can formulate a mixed integer linear program that's going to allow us to map the inputs to the outputs of a trained neural network. I think it's important to do a pause here and explain that we're not talking about optimization to train the neural network. We're assuming that the neural network was trained. And what we want to understand is the connection between inputs and outputs. So we are creating an optimization model where we're going to use the parameters of the trained neural network to correctly describe its behavior. And by solving optimization problems over it, we're going to be able to evaluate the neural network and do other things with it. In this case here, we're going to be able to compress the neural network. Now, for a single ReLU in this neural network, the formulation between inputs and outputs is going to look like something that I have on my screen right now, where we're going to have variables representing the input, decision variables representing the input, decision variables representing the output of every neuron, and decision variables for the pre-activation output. And in addition to that, and I mean, we could spend an entire talk just discussing this formulation and the many ways in which we can improve it and understand it. What I really wanted to save from this slide is the fact that we have this binary variable z, which is going to tell us whether the neuron is active or inactive in a given solution, given the values of the variables associated with the input and the outputs coming out of the neurons. Now, the way that this binary variable is going to help us do this modeling here is that when this binary variable z equals 0, the output equals 0, and that happens when the pre-activation output is smaller than or equal to 0. So that's one phase. In the other phase that we have here on the right, the binary variable z is 1 because the pre-activation output is greater than or equal to 0, and the output equals the pre-activation output. Now, what we have in front of us here is we have two objective functions, and we have means to define the constraints of this optimization problem. And I can't see any of you because all of your cameras are turned off right now, but I can imagine that maybe one of you would stand up now and be outraged by what I'm proposing. Because if you think about it, I'm talking to you about solving two mixed integer linear programming formulations per neuron. And that's not going to be cheap if we're talking about neural networks that are sufficiently large to make this problem interesting in the first place. And well, we know that. And in any case, we really wanted to have a taste of how much we could do with it. So in prior work, what we were able to do to make up for that was that once we identified that the upper bound for the maximization problem was negative, or the lower bound for the minimization problem was positive, we would just interrupt the solver because we had enough information about the stability of the neuron. And this is what we got in terms of runtimes. For two hidden layers of 25 neurons each, we would solve it in 30 seconds. For two hidden layers of 30 neurons each, of 100 neurons each, it would take about 400 seconds. Now, this is not a slow computer that I'm talking about. This is in fact slower than training a neural network in that same computer, which is not great, but it was a proof of concept because we were able to compress something. So now there's a couple of insights that we can use about this compression problem that are going to help us solve this problem faster and in larger neural networks. The first one is that we're solving all these problems over the same feasible set. Basically, our constraints here are mapping the network inputs to their outputs. So as we're solving this problem for a neuron, we're going to use the same constraint set for the other neuron. It's just a matter of changing the objective function. And even for the same neuron, we're basically just switching the objective function, the sign of the objective function, and solving it again. And the other observation here, and that's a paradigm shifting one, is that it's easy to certify that a neuron is not stable. So if I want to know that a neuron is not stable, I only need two inputs to the neural network. One, that when you send through the neural network, you can show me that the neuron is active right now. And another one, which when we send through the neural network, we're going to see that the neuron is inactive right now. And we're done. I mean, we have seen the neuron being active, being inactive. There's no way the neuron is going to be stable. Now, the issue is when we want to do the converse, when we want to show that a neuron is stable, because that means that we have to certify that we solved the optimization problem and that there is no way that we can find a better output, like a smaller or a greater output for the pre-activation output. And now the thing is, when you put these two observations together, if you think about it, we can use one network input to certify multiple neurons. So what we're going to do here is we're going to rethink this optimization problem as we want to find an input that certifies as many neurons of unknown status as possible. So we have this mysterious neuron. We don't know what to do with this neuron, but we do know that we can test any input from a given bounded set. And what we want to know is whether for certain neurons, their pre-activation output can ever be greater than or equal to 0. And we want to know that for a set capital P of neurons that have not been active yet. And there will be other neurons for which we want to know if this pre-activation output is smaller than or equal to 0, because we have not seen that happening yet. That's the set capital Q of neurons that have not been inactive yet. So we're putting this together now. So we have the set P, the set Q, and we have these binary variables P and Q corresponding to the neurons in those sets. And we want to find an optimal solution for this objective function instead. We want to maximize over all the possible inputs of the neural network, the number of neurons that we're going to see in a state that we haven't observed before. Now, one thing you can imagine here is that we actually don't have to have every neuron in every one of the sets, because with a single input, we can tell if a neuron is active or inactive and just put a neuron in the other set. Now, what happens if we try to solve this problem and the optimal solution has a value of 0? If we get that, it means that for every neuron in the set P, we have that neuron is stably inactive. We try to make it produce a positive pre-activation output, and we couldn't. And then for every neuron in the set capital Q, we know that they're stably active because we tried to find a negative pre-activation output, and we couldn't either. But if by solving this problem, we get a positive solution, then we're one step closer to identifying all stable neurons, because we will be ruling out neurons for which we're going to see one of the states that we haven't seen before. And now, the interesting thing here is that we actually don't have to solve this optimization problem more than once, because we only need to solve this problem to optimality if we are going to find a solution of value 0, because in that case, we are certifying that the remaining neurons are all stable. If along the way we find any solution with a positive value, we know that the neurons that have a different status there are not going to be stable, and we can just remove them. So what we can do here, thinking as an integer programmer, is let's solve this problem. And every time we come across a solution where we have seen one of these variables P and Q turn to 1, we're going to remember that. So basically, those are neurons that are not stable. And let's just add some lazy constraints to say that this binary variables P or Q are no longer going to be positive, because we have already identified a neuron with that status. In doing that, we're going to extend the solution of this problem all the way to the point where the optimal solution that we're going to find has a value of 0, by cutting off all the solutions that we get along the way, but remembering what those solutions were telling us about the neurons that are not stable. And what we can also do here is relax these binary variables that we created, the variables P and Q, by just using the integrality of that variable Z that exists in all these formulations that optimize over the neural network in mixed integer linear programming formulations. So here we have everything that we need. We have the objective function, we have the constraints, and every variable P is going to be bounded between 0 and Z. Every variable Q is going to be bounded between 0 and 1 minus Z. And then there is the cherry on top of this cake, which is an observation made in Montreal. So Jason Zhou was a student in Montreal some years ago and worked with Matteo Fischetti. And this is actually something very simple, but until someone says it, it's not a fact. So one of the reasons why mixed integer programming is hard, in fact, one way in which you can prove that mixed integer programming is hard, NP hard, is by the fact that finding a feasible solution for an MIOP formulation is NP complete. Now, in the case of these formulations that we're talking about in neural networks, if it's easy to find an input for the neural network, it's easy to come up with a solution for this formulation. After all, for any inputs that you can think of, you're going to automatically have what are the status of the neurons, what are the outputs of the neurons, and that's going to define the solution, a solution of this MIOP formulation, which doesn't mean that we can efficiently solve this problem. I don't think so, but at least it means that it's not hard to find a feasible solution. And feasible solutions, as we have seen in the previous slide, are going to be very important for us. And if we want a feasible solution and we want to leverage the fact that we have the solver doing a lot of computation for us, what we can do here is use the input coming from the linear relaxation. So the linear relaxation will be a solution, we will define an input to the neural network, for which the binary variable z might have fractional values, but the input is nevertheless valid. So if we just restrict the MIOP formulation to that particular input, to those particular values for the x variables, that's going to automatically define a feasible solution, a single feasible solution for the rest of the formulation. And we can argue to a certain extent that this solution is guided by the objective function, except for the fact that the variables z are relaxed. And the great thing about this is that we can get one of those at every node of the branch and bound tree. And what we observed in the experiments is that we would get to a point where we're trying to prove that these two last neurons are either stable or not stable. And by just using the linear relaxation, we were able to cut the tail of the runtime considerably. And also when we tried to just generate a random value, a random input in place of the linear relaxation, it wasn't as good. It was actually basically the same as not using anything. Now, when we look at the runtimes now, they're very different, which is great. So here is just a comparison for the sizes that we mentioned before of what happens with the new approach in comparison to the work that we published last year. Now, I'm using color here to talk about the amount of regularization used to train these neural networks. I'm not going to discuss that right now, but we're going to see that later. But what I want to point out here is the speed ups that we're obtaining for these different configurations. So when we divide the runtime before by the runtime after, the median values for the smallest configuration is 15 times. And this goes up to 39 times when we talk about a larger configuration. So basically this is orders of magnitude faster, and it gets better and better as we work with larger and larger neural networks. Now, I have told you that we're going to use the stability of neurons. I have told you that there is a way to tell if a neuron is stable or not, but I haven't told you yet how we can make the neural network smaller when we know that information. And when we identify these neurons and we know that what kind of stability they have. So here we're going to talk about 4 different cases that could happen and that would allow us to compress the neural network. The first one is when we have a neuron that's stably inactive. So if we look at that neuron in isolation, the output coming out of that neuron is always 0, which means that that if we remove this neuron, we will have no effect on the pre-activation outputs of the neurons in the next layer, and the neural networks are going to remain essentially the same. Now, we may also wonder what happens if the entire layer is stably inactive, which is not something that we're going to see happening very often, but just for the sake of understanding what happens. If we're in a situation like that, the output of the entire layer is a vector of zeros, which means that no matter what input you send for the neural network, we're always going to get to an intermediate state that's always the same. And as a consequence, the output of the entire neural network is constant. We're always going to get the same output, which means that we can remove all the hidden layers. But in fact, this is a case where the neural network that you have a very bad neural network which basically just spits out the same thing all the time. So we're not going to expect this to happen. But one thing that may happen, and we actually have seen this in the experiments, is that we may reach a situation in which an entire layer is stably active, or at least what is left of the layer is stably active once we remove the stably inactive neurons in the layer. When that's the case, the output of the layer is a vector defined by an affine transformation of the vector of inputs. And if we look at any neuron in the next layer, we can redefine the pre-activation output of that neuron to be a linear, an affine function on the inputs, on the outputs coming from the preceding layer. Now, basically, we can rewire the neural network to bypass this stably active layer and then remove this layer, because we just changed the other parameters in such a way that we're going to obtain exactly the same outputs with the neural network. Now, we may also have just some neurons being stably active. So in that case, for those neurons at least, we have an affine transformation of the inputs coming out of their outputs. And in this case, if the rank of the submatrix of the weights of these neurons is smaller than the number of those neurons, we know that the outputs of this, the pre-activation outputs and the outputs themselves are linearly dependent. So there is some way by which we can just change the parameters of these neurons to induce the same impact in the neurons in the next layer, and while removing the neurons that are redundant. So that might allow us to remove some neurons of the neural network just to remove this rank deficiency that we're seeing, that we have seen in a particular set of neurons. So, all right. So I have told you that we're going to look at stable neurons. I told you that we can do that we can solve an optimization problem. And I have told you that if we are able to do that, if these neurons are there and we found them, we can do something to make the neural network smaller. Now, the final question here is whether we're actually going to find stable neurons when we train a neural network. And what was found out previously is that if we use L1 regularization, any amount, when you're training a neural network, we're going to find some level of stability. And in fact, this has been used to make it easier to verify neural networks or to train them against robust, to make them robust and train them against adversarial examples. So, and what happens in this case is that as we're using L1 regularization, we're going to drive the weights down much more than in the case where we use L2 regularization, for example. And if the bias is negative, that means that very likely we're going to have a stably inactive neuron because the weights are not sufficiently large to change the pre-activation output to be positive. Whereas we may also have these weights going down and the bias being positive, in which case the pre-activation output is likely to remain positive for many neurons just because the weights are not sufficiently large to have a different impact. Now, the other important thing to mention here is that if we use some, but not too much regularization when we're training a neural network, we actually get better accuracy. Which brings us to our experiments now. So the first thing that we tested is what happens on MNIST classifiers, how many neurons we can remove from them. And what we did here was we trained neural networks with no regularization. Then we trained them with so much regularization that we were actually past the ideal point. We were basically getting the same accuracy as not having regularization. Basically, like we added so much that it's just not worth adding more. And then we looked at what happens right in the middle when you have some regularization, but not so much, and this is what happened. So we started with the largest networks that we had before, and we kept increasing. So in this first table here, I have neural networks with 100 neurons per layer, but I'm increasing the number of hidden layers from 2 to 5. So you can see that with no regularization, we have no compression. With a lot of regularization, we're removing about 25% of the neurons, which corresponds to about 40% of the connections. Now, right in the middle here, we're still having some compression. And when we look at the accuracies, you can see that the accuracies for the first and the third column, they're about the same. And right in the middle, we're having the cake and eating it too, because while we're training, we're not using so much regularization. So the accuracy ends up being higher. And once we were done training with that amount of regularization and getting this better accuracy, we can actually remove about 15% of the neurons. So like it's a great deal. Now, in the second table here, I'm showing to you what happens when we keep 2 hidden layers, but we double the width of those layers. So we go from 100 to 200 and all the way to 800 neurons per layer. So you can see the figure is about the same, but for the most extreme case here, we actually timed out. After 2 hours, you couldn't identify all the stable neurons of these networks. And when we look at the run times, here you can see that for 2 hidden layers of 100 neurons, now it takes no more than 14 seconds, whereas before it was taking about 400 seconds. And we have similar figures when we're talking about doubling the layers, but keeping just 2 hidden layers. And what's interesting here is that when we compare these 3 columns, the harder one is the one in the middle. So we can have the cake, we can eat it too, but it's going to be a very expensive cake. So if you look at the last line where we have runtimes for everyone, it takes 400 seconds with no regularization, 130 with a lot of regularization, but 1800 with the medium amount. Which brings us to the second point. It's easier when you have more and more regularization past that point. Now, the other interesting thing that we found is that when you're applying L1 regularization, no matter how much, we can associate, the number of neurons left when you compress a neural network is going to be proportional to the accuracy of the neural network. So you can see that it's not so much guided by the regularization. So neural networks, for neural networks with the same amount of regularization, we're going to see the ones with less neurons removed as being the ones that are more accurate. And you can see these empty balls, the ones with like the white interior, they're the ones with no regularization. So they're just not in this, they're just not part of this regression. And here we have like a coefficient for determination of 64%, which is very good. Now, the other experiment that we did was to look at MNIST autoencoders, but we did something different there. We actually looked at what happens when we use way more regularization, because we were trying to find extreme situations, such as a layer being completely stable. So what we observed when we put a lot of regularization is that the first 2 hidden layers are going to be folded. So we're going to see that the entire layer being stable and we're going to be able to fold it. And that happens before or about the time that the loss is doubling in terms of how much regularization we're adding. So in this first table here, we have autoencoders with 3 layers, and we're varying the size of the bottleneck layer, the width of the bottleneck layer. So we have no regularization, some amount of regularization that just worsens the loss a little bit, and 10 times more regularization, which basically doubles the loss, roughly. And what we observe now is that when we add so much regularization, but the loss is not going down so much, it's not going up so much, but we're removing between 5 and 10%, like we're removing between 90 and 95% of the neurons of the neural network. And when we look at the results for when we vary the width of the other 2 layers and we keep the bottleneck the same, we're seeing similar figures as well. And when we look at the run times, that's where things get even more interesting, because I mentioned that when we use so much regularization that we're back at the original accuracy, the run times are a bit lower. Now, if we add a lot more of regularization, it gets a lot easier to solve this problem. It's easier to tell which of the neurons are stable. So you can see that for the first table, basically it always takes 3 seconds. For the second table, it takes between 1 and 10 seconds, which in some cases is speed up of more than 100. Now, this is basically the easiest case here. So we're basically approaching the end. And to summarize things, we presented here a general purpose exact compression method, which scales to network that are large enough for practical use, which is great, runs faster than training the network, which is a first, and finally, and in a nutshell, what we're doing here is we're removing and merging neurons, folding layers, and collapsing the network, but that's a very unlikely scenario of like when you actually didn't train the network very well. When we're doing that when the neural networks are trained with L1 regularization. We need that to induce some stability, but we're looking for whether there are other ways in which this stability can be induced as well. Why we're doing that? Because the stable neurons have a linear behavior, so we can simplify that part of the neural network. A good neural network has nonlinearity, and in the parts where it doesn't have nonlinearity, we don't need it to be so large. And how we're doing that? By solving an optimization problem, because whenever you need to solve a complex problem, MIP is there for you. With that said, thank you very much. I'm just going to briefly show the references. So the first paper here is the preprint with this work. The second one is the prior work. And then there's some related work on linear regions that touch on this, on how you can understand the neural network as a piecewise linear function and how we can measure this expressiveness and approximate it. Thank you.
Thank you very much, Thiago, for the nice talk. It brought us a new view to the compression problem. Thank you very much. It was very, very insightful.